Hey guys, welcome back. Also, welcome to anyone who happens to have subscribed via Reddit, because I know there was a post on there by someone from my class, so thanks for that. Anyway, so here's our new topic for Area of Study 1 for Unit 3, all to do with fields. Now we're talking about electric fields. Okay, so if you haven't watched the videos on gravitational fields, you might like to go and do that. Because that sets up the groundwork for basically explaining what a field is. So go and watch those ones first before you watch these ones. Okay, so the electric field. Here's our key knowledge focus for this video. So basically we're just going to describe electricity using field model. We're going to look at the shapes of electric fields and the directions that the fields point in. And we're going to talk about charge a little bit. Okay. So, what is the electric field? Basically, just like the gravitational field, the electric field is just a region in space. Okay, so it's a region in space surrounding a charge rather than the gravitational field being a region of space that surrounds a mass. Charge, like mass, is an inherent property of an object. Okay, so just as, atoms, molecules, which compose bigger objects. Okay, these things have mass. That's just a property of that particle. Charge is also just a property of the particle. Okay, it's just a thing that a particle has. So things like electrons. Electrons have what we call a negative charge. Protons have a positive charge. Neutrons have a neutral charge. Okay, they don't have either a positive nor a negative charge. So things that exist have either a charge or not. Okay, and the charge can be positive or negative. Now, just like with the gravitational field, if you put an object with mass inside a gravitational field, it will experience a force, okay, because mass is the property that reacts to a gravitational field. In an electric field, if an object has charge, and you place it in an electric field, it will experience a force as well. Okay, charge is the property that reacts to the field rather than mass. Okay, so even if an object has mass and you put it in an electric field, if it doesn't have any charge, like a neutron, it won't experience a force. Okay, so the electric field exerts a force on objects which have a charge. Okay, charge is the thing that we're talking about now. Okay, an electric charge. Just as we said before, okay, electric charge can either be positive for protons, negative for electrons, or neutral. Okay, there are these subatomic particles called quarks, which are the things that make up protons and neutrons. Okay, and each of those has something like 1/3 of a charge or 2/3 of a charge or something like that. And we're talking about like a unit charge here. We'll cover this in another video. But for the most part, we're going to be talking about protons and electrons. Okay. Just as we said before, objects with zero net charge won't experience a force when placed in an electric field. Okay, so for example, you've got neutrons or atoms in general. Atoms generally have a neutral charge because the number of protons equals the number of electrons and the charges sort of balance out. Okay. And you might remember from year 11 that electric charge is measured in what we call coulombs. Okay, and we give that the symbol capital C. Okay, just like mass is measured in kilograms. We're talking about charge though. Okay, forget about mass for now. We're always talking about charge when we deal with electric fields. Okay, so what are the shapes? Well, here's a basic electric charge. Okay, it's a positive charge of some kind. It could be a proton, could be just something else with a positive charge. This is what the field looks like. Okay, so the field sort of radiates outwards from that charge. Okay, we say that if it's like a proton or something, we say that the field is exerted radially outwards. It's not uniform. Okay, the further away you go, the weaker it gets. The closer you are to the charge, the stronger it gets. as indicated by the field lines. Okay, the more closely spaced the field lines are to each other, the stronger the field. If the field lines are sort of further spaced, then the field is weaker. Okay, so this is for a positive charge. Okay, positive charge radiates its field outwards. Okay, so all the field lines point away from the positive charge. All right, so for example, this would be a proton. Okay, the opposite of this would be a negative charge. Okay, something maybe like an electron or something else with a negative charge. Okay, the only difference really is that the field lines point towards the negative charge. Okay, this is just a convention. Okay, by convention, field lines point away from positive charges, but towards negative charges. Okay, that's just the convention that we use. It just happens to be set up that way. All right, but basically between the positive and negative charges, they look exactly the same, except for the direction of the field lines. Okay, so that's pretty easy to remember. Okay, you just got to remember which one does what. Okay, away from positive towards negative. Okay, and this might remind you of the shape of a gravitational field surrounding a mass of some kind, like a planet or something. Okay, the negative charge basically is exactly the same shape as the gravitational field. Okay, so you'll start to notice that there are a lot of similarities between gravitational and electric fields. So just keep that in the back of your mind. There are a lot of similarities. This one here being the first similarity. Okay, the only difference between gravitational fields and electric fields really is that charge can be positive or negative, whereas there's only sort of one kind of mass. There's not like a positive mass and a negative mass. Okay, so there's only one kind of gravitational field. With electric fields, there's basically two kinds. Okay. All right, so that's the shape of what we call a point charge. Okay, charge, when we talk about charges with electric fields, we don't consider like a specific volume in space. We just pretend that the charge is at a single point and all of the charge is concentrated at that single point. Whereas when we deal with sort of gravitational fields, we have to consider the size of the object as well. Don't have to do that with electric fields. Okay, with electric fields, there's no sort of center of mass that we have to deal with. We just pretend that all of the charge is concentrated down to a single point in space. Okay, and the electric field is sort of being exerted from that point. Okay. All right, now we can place charges sort of close to each other like we can with masses. So you might remember from the gravitational fields videos, showed you a picture of the field surrounding, say, the Earth and the Moon. Okay, kind of looked something like this one here on the right, except the field lines were pointing towards the masses. Okay, we can do the same thing with charges. We can put some charges close to each other and then draw the field around those collections of charges. So on the left here, you've got a positive charge paired with a negative charge. And you just got to remember the field lines point away from positive charges but towards negative charges. So if you're presented with a question and it says draw the electric field surrounding two charges like this, you just got to make sure you're drawing the field lines out of positive and into negative. Okay? And this picture here might remind you of if you've seen a magnetic field around a bar magnet or something like that. It's very similar. Okay, so just try and commit these pictures to memory. You've also got here on the right electric field surrounding two positive charges closely spaced together. You could do the same thing for two negative charges closely spaced together, except the field lines would point towards the negative charges rather than away from them. Okay, there you go. Okay, these are really the only setups that you need to remember. Okay, so you've got point charges, single point charges, positive and negative. You could have two charges spaced closely together, such as these. And you can also have one more. Bit of lag, sorry. Whoop. Okay, one more type of field, electric field. This is the field between what we call two parallel plates of charge. Okay, so these might be some kind of metallic plates. Metal is one of those types of material that can be charged very easily. So you might be able to charge one plate more positively than the other one. and the field that it would produce would look something like this. So you can consider the positive plate as being composed of a line of positive charges, each one of them exerting its field outwards. And you can consider the negative charge as being composed of a line of negative charges. Okay, and it would sort of pull the field down towards it, I guess you could say. Okay, so when we see a setup like this, two parallel plates, each one of them having an opposite charge, the region in between, the middle, indicated by the red box here, that is what the field would look like. And we say that's a uniform electric field. Okay, it's uniform because the field is pointing in the same direction and the strength is equal anywhere in the field. Okay, so the field strength there would be equal to the field strength here, would be equal to the field strength here, would be equal to the field strength here. Okay, so it's uniform, the field strength is the same everywhere, and the direction is the same everywhere. Okay, except for the edges, but we can ignore that. Okay, we're just looking at this sort of bit in the middle here. Okay, so those are the types of shapes of electric fields that we'll be dealing with. So you've got point charges, you could have charges that are spaced closely together, or you could have these sort of parallel plate setups. Okay, and that's it. That's the only fields that we've got to consider, the only shapes of fields that we've got to consider in this topic. Okay, so question, why do lines point different directions for positive and negative charges? Okay, why is the field point outward from positive and inwards for negative? It's just a convention, okay? It's just what we do. It's just how it is, okay? Just someone came up with it one day and that's how it's been ever since. Although another way to think about it is you can think of the field lines representing the direction that a positive charge would experience a force when placed inside that field. Okay, so if you were to place a positive test charge in a field from a positive charge, then it's going to be repelled. Okay, positive charges repel other positive charges. So if you were to place a positive charge, so let's say there's a positive charge here, it's exerting its field out into space around it. You place a positive charge somewhere nearby, what's going to happen to this guy here? Well, he's going to get repelled. So by convention, the field line would point away from this sort of central positive charge. Okay, you could do the same thing replacing this central positive charge with a negative charge. Okay, and you might recall that positive charges are attracted to negative charges. So instead of the field pointing away from that negative charge, this test positive charge here would be attracted. So you say that the field line points towards the negative charge. Okay, so that's how we use that convention. Okay, the field points away from positive charges because that's the direction that a positive charge would move when placed in that field. Okay. Cool, so here's a question. Describe or draw what would happen to the test particle in the following situation. So the test particle is sort of this one hanging around inside the field. Okay, so let's look at the first picture. So we've got a positive charge in the middle, exerting its field outwards. If you were to place a positive test charge in that field, well, just like in the previous slide, we know that it would be repelled. It would follow the field lines. Okay, so it would go sort of off that way. All right. Next picture, you've got a negative charge exerting a field. Okay, field lines point towards the negative charge. Which direction would the positive test charge move? Well, positive test charges follow field lines. So that positive charge would go that way towards the negative charge. Cool. All right, what if we put a negative test charge in the field? Well, positives and negatives are just opposite of each other. So they'll do the opposite of what they would if it was positive. So if you put a negative test charge in a positive field, it would go the opposite direction to the field lines. Okay, so it wouldn't go off that way, it'd go that way. Okay, and even if you just remember that negative charges are attracted to positive charges, you can very easily figure out which direction it's going to go. Next picture, okay, negative test charge in a negative field. Well, both are negative, so it's going to get repelled. It's going to go off that way. Cool. All right, last one. So we've got this uniform electric field between two parallel plates. Which direction will these test charges move? Well, you just remember, positive charges follow field lines, negative charges go the opposite direction to field lines. So this positive charge is going to get forced down that way, negative charge will get forced up that way. And again, you can just remember it as being, positive gets attracted to negative, positive gets repelled by positive. So even if you forget about the field lines, you just know that this positive charge is going to get attracted to the negative side of this parallel plate setup, and the negative test charge will get attracted to the positive plate. Pretty straightforward, I think. Right, at this point we're going to talk about something called monopoles and dipoles. So you may have heard this term before if you do chemistry. Basically, a monopole is just a single electric charge. And we'll talk about this later on when we do magnetic fields. That's all a monopole is, okay? It's just a single positive or negative charge. That's it, okay? If you put two charges close to each other, a positive and a negative charge close to each other, you can call that setup a dipole, okay? And that's what's going on here, okay? It's just a positive charge next to a negative charge, okay? And they're sort of coupled together, and they sort of move around together as well, all right? Where do you see this in sort of real life? Well, one place you can see it, and this is relating to chemistry now, certain molecules can be considered an electric dipole. Okay, so for example, you've got water here. Okay, this is the water molecule, H2O, so the white balls are hydrogen and the red ball is oxygen. Just the way that the sort of electrons are shared between the atoms, it turns out that the oxygen atom ends up being more negative because it attracts more. I won't say attracts. There are more electrons surrounding the oxygen atom than there are surrounding the hydrogen atoms. Okay, on average, the electrons spend more time around the oxygen atom than they do with the hydrogen. So overall, the molecule itself is skewed in its charge, so that the oxygen atom is, or the region around the oxygen atom is more negative than the region surrounding the hydrogen atoms. Okay, so this is like saying this is a negative charge here, there's a positive charge here. There you go, that's a dipole. Okay, compare that with the previous picture. You've just got a positive charge next to a negative charge. That's basically what's going on inside that molecule. Okay, same thing with hydrogen fluoride. All right, I don't know which one's which because I don't do chemistry, but one side of the hydrogen fluoride is more negative than the other side. Okay, so you can consider this being a dipole. Okay, that's the negative side, that's the positive side. It's just a positive charge next to a negative charge. All right, so there exist electric dipoles in nature, okay, mainly in the form of molecules. Okay, that's it, no more chemistry. We're done with chemistry. Cool. All right, so that's it for this video. Let's do a summary. So basically, charge is an inherent property of an object, like mass. When we deal with electric fields, we're talking about the field produced by a charge. We're not talking about gravitational fields, which are produced by a mass. Okay, so ignoring mass for the most part. Okay, charge can either be positive or negative. Okay, protons are positive charges, electrons are negative charges, and charge is measured in this unit called coulombs, which we give the symbol C. Charges produce an electric field. Positive charges exert fields radially outwards. Okay, the field points away from positive charges, and radially inwards, okay, points towards negative charges. We can also consider the field between two oppositely charged parallel plates, and that is a uniform electric field. Okay, so remind you, that is like this. So this plate is positive, this plate is negative, and the field lines point towards the negative plate like that. Okay, and that region between the plates is uniform. Okay, the field is the same strength everywhere and points in the same direction. Like charges repel, so positive repels positive, negative repels negative, and opposite charges attract. Positive attracts negative. Charges can either be monopoles or dipoles. Okay, so remember, monopoles are basically just single positive or negative charges, and dipoles are when you have a positive charge next to a negative charge, and they sort of couple together. And just by convention, field lines point away from positive charges and towards negative charges. And you just got to remember, we're talking about a field which is a vector. Okay, so go back and watch the gravitational field videos. That explains how it's a vector. If you've got multiple charges sort of floating around and you want to work out the field at a point in space, then you have to sort of vectorially add the fields from each charge at that point. Okay, so you just got to remember that the field is a vector. It has a direction. Cool. Right, so there's some summary questions for you to attempt yourself. Okay, it's just drawing the field surrounding two negative charges or two positive and two negative charges at the corners of a square with charges diagonally opposite each other. Okay, have a go at drawing them. And that's it for this video. Okay, so see you next time.